In part 3 of lesson 12.2, we'll finally finish the lesson. We talked about a very exceptionally important theorem. You can see it's highlighted at the top of the screen. It's known as the nth term test for divergence. If the limit as n goes to infinity of that a sub n, the nth term of a sequence, does not equal 0, then the series a sub n diverges, or the explicit formula a sub n, which you'd see inside of the series, inside of epsilon. That's wonderful, but look right below it. If the limit as n goes to infinity of a sub n equals 0, frankly, we don't know if that series converges or diverges. We'll say further investigation is needed. And we're going to take a look real quickly at 4 problems that are going to allow us to do some real quick tests. We'll either say we have convergence, divergence, or further investigation needed. What you want to do, even though this is a series, take that explicit formula inside. It's the nth term of the sequence as you'd go term by term and then add them together. But as n goes to infinity, using n behavior, it's as if that negative 8 isn't there and n would cancel with the 4n. You will arrive at 1/4. We now know that this series diverges by the nth term test for divergence. And we can say that quickly, and we're done. Take a look at our next problem. As n goes to infinity, if we had 1 all over that cube root of n, plug in infinity down below, the cube root of infinity is still infinity. 1 over something super large goes to 0. We don't know. Right now we don't know. We'll know shortly in a couple of lessons, a very quick way how to tell what's going on. But for right now, we'll just say further investigation is needed. Very similar problem right here. Limit as n goes to infinity of 1 over n squared. Well, 1 over something very large goes to 0. Likewise, we'll say further investigation is needed. For this last one, as n goes to infinity of e to the n all over the natural log of n, you can quickly realize you have infinity over infinity, which is an invitation to do L'Hopital's rule. So we'll say the limit as n goes to infinity. The derivative of e to the n is e to the n itself. The derivative of natural log is 1 over n. And tell you what, dividing by a fraction is the same thing as multiplying by its reciprocal. And we can see quickly we'd get e to the n times n. This would be e to the n, which is infinity, times infinity, will be infinity. Look at the top of the screen. If your limit of that nth term is not 0, we can say our series diverges. So arriving at infinity is really saying we do not arrive at 0. So we can say quickly that this series diverges. All right, take a look at our final page. If you have 2 convergent series, a sub n and b sub n, which sum to a and b respectively, look at Roman numeral 1. When you add the 2 series, you would arrive at a sum of a plus b. If you have a constant inside, you can factor that constant out. It would be like c times the series of a sub n. So that will arrive at c times a, another convergent series. If you're subtracting your 2 series, you'll arrive at a minus b. Well, looking at this next example, just want to point out that as you're investigating the first part of that series, that might look a little strange at first. Take a look at term by term what's happening. As I plug in n equals 1, 1 minus 1 is 0, and 4 to the 0 is 1, so I'd have 3 all over 1. Then, this is a series, I'm going to add term by term. Plug in a 2, 2 minus 1 is 1, so I'll have 4 to the first. Up here I still have a 3. Plug in n equals 3, and quickly we'll arrive at 3 minus 1 is 2. You got 4 squared, and so on. What's really happening? I hope you're going to notice this is a geometric series. It's a geometric series. Whenever you see that nth power raised up in this fashion, you can very well suspect that we're going to deal with repeated multiplication from term to term. That's what a geometric series is all about. Hopefully you can agree that our first term would be a 3. And what are we multiplying by to get each subsequent term? I hope you can see that it looks like we're going to be at 1/4. You can kind of see that 1/4 kind of hidden in the formula. Well, if you look back on the earlier portion of the geometric series, you will have convergence, and you're going to arrive to a sub 1 all over 1 minus r if your common ratio, what you're multiplying to each subsequent term, in absolute value is less than 1. Well, that's what we're seeing here. The absolute value of r is in fact less than 1. So our sum should be a sub 1 all over 1 minus r, so that's 3 all over 1 minus 1/4. We'll get 3 all over 3/4, and that's really 3 times 4/3. This actually arrives at a 4. So this geometric series right here is going to be converging to 4. From example 1, look back at our first video, you're going to see this was your telescoping series that arrives at 1/3. It will converge to 1/3. Where is this sum of the series going? Well, to 4 and 1/3. Finishing up. Let's just say you have a convergent series, but then you add to it a divergent series. That sum is going to be divergent. As you're looking at this last example, this first formula is going to be indicative of a geometric series. You can see that n minus 1 up there. You could write out a few terms if you really wanted to. Find the first term, find your common ratio. I think you can do that pretty quickly. But this other part of the problem, sigma of 1 over n, is a divergent harmonic series. The harmonic series is one of the most famous series in this chapter, and we're going to be able to say it diverges as a matter of fact. So therefore, this series diverges. One part of its formula, has a divergent series within it. So regardless of whether your first series is convergent or divergent, it really doesn't matter. Well, that wraps up our lesson. Best of luck to you.